you've probably been going through some of the conservation momentum stuff, and you're like, oh, this is kind of plug and chug, kind of formulaic. Um, yeah, you're like, nothing's challenging me. Well, of course, we have stuff for that. So here I'm just gonna go through the second level of the law of conservation momentum, and that is what is true with the fact that momentum is not only conserved in one plane, it is conserved in both planes. All right, so that's what we're going to focus on here, and that's the fact that momentum is conserved in both planes. All right, so that means that you're going to be able to say, okay, in the x plane, I see you, you're in the x plane, we're going to conserve momentum. All right, good to go. Y plane, no, I see you too. We're going to conserve momentum in that plane too, which means that we can do, yeah, you guessed it, angled problems. Oh, yeah, I love those, love those, love those. All right, so I'm going to do a super straightforward example, one of my favorite pastimes, and that is billiards or pool to the, less educated out there. So let's just say we're playing some billiards and we are going to hit a ball, and I have no idea what the mass of a billiards ball is. So I'm just going to say it is some unknown mass, okay? And so this is the cue ball here. All right, and we're going to hit it with a velocity of 10 meters per second. All right, and so it's going off flying, and we're going to aim it so that it hits the 9 ball. Okay, this is not the mass, it's just the fact it's the 9 ball. Okay, you're going for the win here, and it is just sitting at rest. Okay, so it's not doing anything. Its velocity is 0. Okay, so this is my before the collision. Now, of course, something has to happen after the collision. So after the collision, we have our cue ball goes off flying here at an angle because I didn't hit like head on, it grazed it. I'm trying to sink the 9 ball. It's not a straight shot. And so this is going off at an angle of 30 degrees here. And then the 9 ball ends up being launched down here at a 60-degree angle to this horizontal plane here. And I have no idea how fast this is going. I have no idea what that is either. And what our goal is to figure out what both of these velocities are. And we don't even have a clue of what the mass of these balls are either. Oh no, oh no, oh no. All right, so that's what our goal is. So we have the before, we have the after, and basically we're just going to use the heck out of the law of conservation momentum because we can do it in both planes. So if we got 2 planes, we can make 2 equations, so we can have 2 unknowns. But wait, we have 3 unknowns because we don't know the mass either. Oh, maybe something will happen with that. I don't know. We'll find out. So let's just we'll start with the x-plane. All right, we'll take it. We'll enjoy the journey. Okay, we don't even know where we're going with this, but we're going to solve the momentum in the x-plane. All right, so this is the x-plane that we are looking at right here. So we're just going to see what happens to the x-plane. Well, if I look in the x-plane, we only have one object moving to start with. All right, so I'm just going to keep track of that one object's momentum. Then afterwards, we have 2 objects that are moving in the x-plane because they are moving an angle. So we've got an x piece and a y piece. So we've got 2 objects that are moving. All right, so mv plus mv. All right, so I'm gonna call this one here just v, and I'll call this like v9. All right, for the 9 ball. I don't want to draw a Q. I'll mess with my head. Okay, so now we're going to just substitute in what I know. Okay, we're just going to take it as far as I can take it. All right, so let's say, if I didn't know the mass, if I had the same mass, this would be boring, right? It'd be boring with the same mass. So let's say that I'm playing with some crazy ball. I'm playing some crazy. So let's include the mass. We'll make this a little easier because as you can see, what happens to mass if they're all the same? They cancel out. But then that's just too easy. I don't want to make this too easy. That's not how I roll. So let's just say this is a mass of, I don't know, 1 kilogram. And this will be a mass of 2 kilograms because it's an illegal set of billiards ball. All right, obviously they're all the same mass. And so you can quickly see here, if all the mass is the same, since masses and everything, it would cancel out. But then, well, that's just boring. All right, so I want to show a super generic one, not a super specific one. So let's say we've got a mass of this is 1, mass of the 9 ball is 2. So now if I go here, I got, well, the only thing moving to start with in the x-plane is the 1 kilogram mass, and it's moving at 10 meters per second. All right, so then afterwards, though, the 1 kilogram mass is moving with an unknown velocity, but the x-plane, we always said that this is going to be cosine. All right, so we got v cosine of 30 degrees. Okay, so that's that one, but then don't forget this guy's also moving the x-plane as well. So plus 2 v of the 9 ball cosine of 60 degrees. All right, so we've got that going on here. So now if I look, I'm like, hey, I don't know v and I don't know v9, so this is currently an unsolvable problem. All right, totally unsolvable. So we go, oh, I give up. No, do not give up. There's no quitting. There's no quitting in physics. So let's look at the y-plane. All right, let's look at the y-plane, and let's just sum the initial momentum and set it equal to the final momentum. Well, if we look in the y-plane initially, nothing's moving the y-plane. So this is a giant 0. But afterwards, we have 2 objects moving the y-plane. This guy's going up, this guy's going down. So we have the same thing. We've got mv plus mv. So I'm just going to kind of cut to the chase here. So we've got this guy, his mass is 1. And then his velocity is v sine of 30. All right. And then we've got this one down here. And since it's going negative, this is going to be a negative momentum, right? Because direction's kind of a thing. So if you look in the y-plane here, this is a negative velocity. So minus 2, because that's the mass, times v9, times sine of 60. All right, so now we have that equation. So we're like, oh, I still can't solve this. I have 2 unknowns. But now I have 2 equations of 2 unknowns, and so this is solvable. And so I'm just going to go through some real quick steps of just substitution, manipulation here. And so you'll just see where I'm taking this. So first I'm going to solve for this velocity of the cue ball. So I'm going to do some algebraic manipulation. And so let's see where I get. I get velocity of the cue ball is going to be equal to, if I bring that over to this side, so this will be positive. So 2 v9 sine 60 divided by sine 30. All right. And if you kind of rearrange this again, you get v equals 3.46 v9. All right, so I'm going to take this, now I'm going to change the color here, because I just want to take that. Okay, so I'm going to take this, and now I'm going to take this, I'm going to slam it into there. Okay, so I'm going to bring it in here, so now we're just doing some substitution. So we are subbing and solving. And so now I have 10 equals 3.46 v9 cosine of 30 plus 2 v9 cosine 60. And so now we look, oh, we now only have the one variable v9. So I can substitute, I can break this down a little bit more. And if you do, you'll see some fancy stuff. And I'm sure you could have subbed in all the trig and seen where this was going earlier, but I just want some simple numbers. So you get 10, this will simplify to be 4 v9. So then I can say, the velocity of the 9 ball is equal to 2.5 meters per second. Oh, that's good to know. All right, so I can just say this guy is 2.5 meters per second. Well, now that I know this, I can then do some more substitution. And I can say, well, let's take that information, and now I'm going to just take this, and I'm going to go whoop into there. And so if I multiply 2.5 times 3.46, I then find that the velocity of the cue ball is equal to 8.66. Repeating. If you kept, now it depends if you kept all your digits or whatever, but you'll figure this out if you do your trig. Meters per second. All right, so that's how fast the other guy's going. So now if I want, I can, I should double check myself. All right, so I should always double check myself before you wreck yourself. So this is 8.6 repeating. All right, so if I take this number and I punch it into this equation, I should get the right answer, and then I can also punch in this equation and also get the right answer. When you do this type of substitution, a lot of times people make mistakes, and they don't take the time to double check themselves, or they miss a minus sign, because, like I said, this right here, this is a minus because it's going down. All right, so you want to take the time to double check all your signs are in order and things like that. But no big deal. Law of conservation of momentum works in the x-plane. It also works in the y-plane. So two equations, you can now handle a situation with two unknowns. And I technically could have made it so the mass was irrelevant, because you notice mass was in every single statement on both sides of these. 0, mass, mass, mass. If they all had the same mass, mass would have canceled out, and so it would have been highly solvable, even with three unknowns in this situation. So good rule of thumb, if you ever have mass and you're like, I wasn't given the mass, don't freak out. Just write the letter M, and odds are it'll cancel out. It's a fun fact of physics. All right, sometimes mass matters, sometimes it doesn't. So that would be a 2D complex momentum problem, and I hope that was helpful. Until next time, I will catch you on the flip side.